Hi guys. So far we've talked about discrete random variables and expectations on them. So let's take an example where I flip a coin, and if I get a heads, you win $1, and if I get a tails, you lose $1. So we could represent this random variable by x, and the probability x equals 1, and this is the amount of your pay, is the probability that x is 1 is a half, and the probability x is minus 1 that you lose $1 is also 1/2. So the expected amount that you're going to make if we play this game is $0. Right, it's right in the middle. But let's say there's another game, which we'll represent by y, and in this game the payoff is $100 rather than $1. So we'll flip a coin. If I get a heads, you gain $100, and if I get a tails, you have to pay me $100. Well, the expected payoff is still 0. So in either game, you have the same expected payoff. It still balances out to 0. But of course, playing game Y is quite a bit more risky than playing the game represented by X. I don't know if too many of you are willing to take the risk of losing $100 to me to play a game like this. So the expectation doesn't measure this sort of thing. It doesn't tell us how risky or how far away a random variable might be from the expectation. So maybe we want to know, how far away will a random variable tend to be from its expectation. So for that, let me give a little motivation. Let's think back to the real number line. So suppose x and y are two real numbers. Then usually the distance, I'll just call it distance between x and y, something like the absolute value of x minus y. Right? That would be the distance between x and y. But another way to think of this is you could take x and y and square it. X minus y, square that so it's a positive number, and then take the square root. So notice that this is always bigger than 0, bigger than or equal to 0. So that's a way to think of the distance between x and y. You square it so it becomes positive, and that way you take the square root and you have a positive number. And this is sort of what we want to do, is we want to see, now then let x be a random variable. We want to represent the distance from x to e of x. So in other words, how far off is x going to be from its expected value? So we want some way to measure this, sort of. And in that last example, if we played the game where you get $1 or lose $1, you can imagine that it's not very far from $0. So the random variable is close to its mean. But in the other example, where that you might lose $100 or win $100, then the random variable, the values it takes, are much farther away from the mean. So we want some way to compute this. And so we kind of use this idea here. But this is the distance of two real numbers. Remember that x, once we take an instance of omega, if we were to actually do something, this maps to r. So this is, x goes from omega to r. So it's going to give us real numbers. And then e of x is obviously a real number, right? When you take the expected value, you just get a number. So what we're going to do is take x minus e of x, and we're going to square this whole thing. Just like here we took the distance from x to y as this squared. But before we take the square root, we want to turn this into a number. So the problem is x is random. And if you just were to do this with x's, you'd get a random number each time you ran an experiment. So what we want is a fixed number that gives us this approximation, this representation of a distance from x to its expected value. So here, to get rid of the randomness, you can take the expected value again. So what's the expected difference here? So this is the actual expected value of x, but this expectation gives us the expected difference. And then, if you like, you can square root it still. So we could square root this whole thing. And what this is called is the standard deviation of x. Although if you notice, the square root doesn't do anything really but scale it up and down. It could have just not bothered with that square root. I mean, maybe we wanted to just know how far do we expect x to be different from its expected value. So if we get rid of the square root, this is called the variance of x. So this, let me use a different color. This is standard deviation. And this one is variance. And this was section 4.5, which we skipped over. So I skipped this section because I wanted a few examples of discrete random variables, which we will compute the variance of those random variables. So we have the Bernoulli, binomial, and Poisson random variables so far. And so we'll be able to find a formula for the variance of those random variables. Okay, so this is the formula for variance, this is the formula for standard deviation. They're both very important formulas that you need to commit to memory. So let's take x to be a random variable. Well, there's another formula for variance that's often handy to use. So let me derive that really quick. So what is the variance of x? Well, it's the expected difference between it and its mean squared. So that we're always getting positive numbers. You want a positive distance, so we square it. And notice if we didn't square it, you just have 0 by linearity of expectation. So let's square this thing out and see what happens. This is the expected value of x squared minus 2x times the expected value of x plus the expected value of, oh, I forgot the 2, minus 2 times x e of x plus e of x squared. Okay, so all we did was just FOIL that, if you like. And now then let's use the linearity of expectation. So this is equal to the expected value of x squared minus, and I'll pull out the constant, so 2 times the expected value of x e of x plus, and the expected value of a number is just that number, right? So e of x squared, this is already just a number, so this is just e of x squared. Well, here I pulled out a constant, the minus 2, but notice that e of x is also, that's a constant, right? Once we've taken the expected value of a random variable, we just get a number. So in fact, I could pull this out also. So this is the expected value of x squared minus 2, so I pull out this e of x, but I still have an x inside, so I still have an e of x. And then plus e of x squared. And notice that here this is e of x times e of x, so that's actually e of x squared. So I get the expected value of x squared minus 2 e of x squared on the outside. So it's e of x times e of x gives us e of x squared on the outside, plus the expected value of x, and then this one squared on the outside. And now I can combine like terms. So I have minus 2 e of x squared plus an e of x squared. So this is equal to the expected value of x squared minus the expected value of x quantity squared, so the square's on the outside. And so this is a formula for variance. And you could use this formula. So what we've derived here is that the variance of x is the expected value of x squared minus the expected value of x, and then with the square on the outside, this quantity squared. So this and this are both equivalent formulas. You could work all these steps backwards. And so if we started with this definition, you'd rederive this definition as well. So these two things are equivalent. Let's see. And maybe I'll go ahead and compute the variance of the linear function of x. And that's about all I'll have time for. So just like with expectations, with variance we're going to have to derive a few properties. So let's say that x is a random variable. And let's let a and b be numbers. So these are two real numbers. And let's compute the variance of a times x plus b. So I took x, multiplied it by some constant, and added some constant. And so with expectation, maybe I'll remind you, the expected value of a times x plus b is equal to a times the expected value of x plus b, right, because it was linear. But let's see what happens to the variance. So this is equal to the expected value of, let's see, which formula should I use? So let's use, I'll square it on the inside, ax plus b squared, and then minus the expected value of ax plus b, and then I'll square this on the outside. Okay, so this is equal to the expected value of, and now we have to square on the inside first. So this is a squared x squared plus 2 abx plus b squared. So all I did was FOIL this. And then we have minus, and now here the square's on the outside. It's this whole thing squared. So here what I'm going to do is first use the linearity of expectation. So we're going to have a times e of x plus b all squared. Okay, and now here the expectation is linear again, so we can just pull out the constants and bring the expectation to the sums. So this is the a squared times the expected value of x squared plus 2ab times the expected value of x plus b squared. And now we're going to have minus, and now let's square this out. So we'll have a squared e of x squared. So notice that when the square's on the inside, it has to stay on the inside. But when it's on the outside, it has to stay on the outside. And so then we have minus 2ab e of x, and then we'll have minus b squared. And so I'm distributing this minus through. So I FOILed this thing, but everything's got a minus in front of it because of this minus out here in the front. Okay, and so what happens? Well, we can cancel some things. We have 2ab e to the x, e of x, sorry, and minus 2ab e of x. So this and this, these two cancel. We also have plus b squared and minus b squared, so these two cancel. And now then here we have a squared e of x squared and minus a squared e of x squared. So I can pull out an a squared from both of these. And then what do I have left? If I pulled out the a squared, here all I have left is e of x squared. And then I'll have minus, and if I've pulled out that a squared into the front, here all I have left is e of x with a square on the outside. And so what is this equal to? Well, this right here is the variance of x. So the variance, let me write in another color what we've derived here. So the variance of ax plus b is equal to a squared times the variance of x. And so variance is not linear. It's not a times the variance of x plus b, like it was for expectation. And this, you might have some sense of why this works. So plus a constant, if you add a constant, all that does is just shift the random variable by the constant. But it doesn't change how variant it is, I guess, or how much it'll deviate from its mean. Right? It would shift the mean up by b because this linearity, and it just shifts the random variable values up by b. And then the a, you're scaling everything by a, so you're multiplying through by a, and so that becomes an a squared, since we squared all the terms inside of the variance. All right, well that's all the time I have. God bless you guys, and I'll see you soon.